Hey there, it's Shannon Matchick-Myers, and today we'll be checking out section 15.2, which covers line integrals, and this is from the calculus text by Larson and Edwards. So basically, we want to understand and use the concept of a piecewise smooth curve, write and evaluate a line integral of a vector field, and a line integral in differential form. So let's warm it on up by representing the plane curve 2 times x minus 3 times y plus 5 equal to 0 by a vector valued function. And if you remember how to do it, awesome. Just go ahead and pause the movie, work on the problem, and then just double check to make sure you got it right. Okay? And then you can move on to that next warm-up that is below. So sorry, it looks like I forgot to number these. This will be our first warm-up and second warm-up, and then we'll go on to the material. All right, so ready? On your mark, get set, go! Pause the movie and warm it on up. Okay, let's see how you did. In order to work this first problem, remember that in general, vector valued functions, this is in the plane, so it would look something like r at t is equal to some x at t times I plus some y at t times I. So what do we have here? We have that y is equal to, isolating y with a little algebra, I believe we'll get y is equal to 2/3 times x plus 5/3. Cool, cool? All right, so now different things you can do. If we go ahead and we let x equal to t, well, then what's y going to be? Beautiful. Y would just be 2/3 times t plus 5/3. Groovy? All right, so writing them, in terms of a function of t, do you see x of t would just be t, y at t would be 2/3 t plus 5/3. Some of these things are so easy they're hard, right? So at the end of the day, putting it together, what we'll have is r at t is equal to t, that's our x at t, times I plus 2/3 t plus 5/3, that quantity times j. And then just so you can match it up, x at t we found by letting x equal t, and that was here. And then y at t we found by plugging in t for x, and so we get this right here. Groovy? And then we happily box up our final answer and move on to the next one. All right, so let's see. Determine whether the vector field f is conservative. If it is, find a potential function for the vector field. So this is in space. And so here, basically, remember, you need to find, if you need to look at your notes, that's fine. You need to find all of these partials, right? All of these partials. So let's do it, because we want to see, they all have, so basically, in general, f at x, y, and z is equal to m times I plus n times j plus p times k. Cool so far? So we want to first check to see if it's conservative, right? If f is conservative. So 1 Is F conservative? Well, what do? We have to check a bunch of partials. So here we go. The first partial of P with respect to Y, what is that going to be? So remember, P is what? 1, right? You could put a 1 right here, 1K. And so here, this right here would be your N. The coefficient to J is your N. The coefficient to I is your M. And the coefficient to K, which remember is, whoops, is just 1. Do a smaller pen there. Okay. Then bring it back. All right, so here, all right, now we're set. So here, let's check it out. So remember, your coefficient to K is just a constant. So dP dy will be 0, right? And which we'll just go through all 6 of them, and then well, the other one that you need to, the other partial you need to find for P is going to be with respect to X, right? And that's also going to be 0. I just wanted to say one thing. Notice that I found the first partial of P just with respect to Y and X, right? Because, you know, P, the Z's always kind of go with K, right? And so I'll be finding the first partials of N with respect to X and with respect to Z, and similarly the first partials of M with respect to Y and respect to Z. So moving along, we'll have dN, the first partial of N with respect to X is going to be, let's see, X squared plus Y squared is raised to the negative 1. We have a Y in the numerator. So we'll have a negative 2xy over x squared plus y squared, the quantity squared, it's in that denominator. And then we'll have the first partial of N with respect to Z is just going to be 0. There's no Z's in that coefficient to J. And now we go to dm, dy will be, let's see, negative 2xy over quantity x squared plus y squared squared. And then we'll have dm dz. There's no z's in m, so we'll get it 0. And what needed to match up? We needed to the first partial of P with respect to Y had to match up to the first partial of N with respect to Z. So for our check, did that happen? So dP, dy, first partial of P with respect to Y was 0. And then the first partial of N with respect to Z was 0, right? So that checks out. Check. And then the next one that needed to match is the first partial of P with respect to X had to be the same as the first partial of M with respect to Z. And so let's see. First partial of P with respect to X was 0, and the first partial of M with respect to Z was 0. So they do, in fact, equal each other. Check. And then let's see, our do you see the other one matches? So our first partial with respect to first partial of n with respect to x matches our first partial of m with respect to y. So check. So therefore, that means that f is conservative. Since, comma. So we're good there. All right, so now, moving right along, let's see what we've got going on. We now need to find a potential function for the vector field. So remember, this is the one where we want to integrate each of those coefficients of the vectors with respect to, the corresponding differential. So basically, we'd want to do integral of m dx, integral of n dy, and integral of p dz. Groovy? Okay, so let's do it. The integral of m with respect to x is equal to the integral of, the integral of x times quantity x squared plus y squared raised to the negative 1 with respect to x. And so we basically need a 2x dx in order to integrate this one. So we need to adapt by a 1/2, right? Groovy, groovy. And so this result, of course, ends up being equal to natural log at absolute x squared plus y squared, which, do you see, if you're adding two squares together, we do not need absolute value, so let's simplify that. And then we'd have plus some g of y and z, some function of y and z, right, that we don't know about. Okay, the integral of n with respect to y will be very similar integral, right? We have y times x squared plus y squared to the negative 1 dy. And again, we need a 2y in order to integrate, so we balance it by multiplying by the 1/2, and whoops, I forgot my 1/2 in my result there for that last one. Bad teacher. All right, so here we go. This will be equal to, here's our 1/2 natural log, and again, we don't need that absolute value because we will have a positive inside the log. And then this would be plus some function of x and z, right? Now, the integral of p with respect to z is just going to be beautiful. The integral of 1, if you need to put a 1 there, dz, which is z plus some function, call it k, of x and y. Okay, so notice that, m and n are the same, so if you differentiate, each of those results with respect to the different ones, you'll get what we had originally, right, once you put them with the vectors. So basically, if we consider that g of y and z equal to h of x and z, and we just let that equal to z, right? And then if we let k of x and y equal to some k, then what we'll have is our potential function, or a potential function for f. Because remember, you want to get something you want to get something where when you differentiate it, you're going to end up, getting what we started with f. And when you differentiate, you lose any constants. So a potential function for f is, and that, by the way, sorry, was our number 2 job. All right, so a potential function for f will be, let's clean up that radical. Do you see that we'd end up having, so f at x, y, and z would equal to the natural log of the square root of x squared plus y squared, using the power rule for logs, plus z plus capital K. Actually, box the whole thing. All right, cool. You feel all warmed up? Awesome. All right, so piecewise smooth curves. So basically, here's some ideas. The work done by gravity on an object moving between 2 points in the field is independent of the path taken by the object. All right. One constraint is that the path must be a piecewise smooth curve. So actually, that's kind of, sorry, I lost my bullets here. And then recall that a plane curve C given by r at t equals x at t times I plus y at t times j, where t is between a and b inclusive, is smooth if dx dt and dy dt are continuous on the closed interval from a to b and not simultaneously 0 on the open interval from a to b. And similarly, a space curve C given by r at t equal to x at t times I plus y at t times j plus c at t times k, where t is between a and b inclusive, is smooth if dx dt, dy dt, and dz dt are continuous on that closed interval from a to b and not simultaneously 0 on the open interval from a to b. So a curve C is piecewise smooth if the interval could be partitioned into a finite number of subintervals, on each of which C is smooth. Example 1, find a piecewise smooth parameterization of the path C. Okay, well, let's check it out. Remember that cosine squared t plus sine squared t is equal to what? Beautiful, 1. So that implies that cosine squared at t would equal to x squared over 16, and which would yield what? It would yield that x is 4 cosine t, right? Sine squared t, similarly, would equal to y squared over 9. So, doing a little algebra on that, we would have y is equal to 3 sine at t. So r at t would be 4 cosine t times I plus 3 sine at t times j. And the interval for this to complete, remember, is going to be from what to what? Beautiful. From 0 is less than or equal to t is less than or equal to 2 pi. Cool? So we didn't really have to go piecewise at all for that one, right? That one, pretty easy peasy. Okay. Let me add, I only had that one and it only had that one interval. So let me go ahead and add in another example. I'm sure you won't mind. Let's say we had something along these lines. Let's see. Graphs. Let's say we had a triangle. All right, so let's say we had a triangle that had vertices, say, at 5, 0, 5, 4, and 0, 0. And let's also suppose that it goes in this direction. Groovy? Okay, so the trick is going to be, okay, what's happening here? We basically have 3 different lines going on, right? Or you can think of it as 3 different vector valued functions. Okay, so I'm going to start t, at this 0, 0, right? So as we go from here to here, right? This line in terms of x and y would be what? Well, you would have y is equal to, the y-intercept is 0, right? And the slope would be 4/5, right? Because you have this point here at 5, 4, and slope is rise over run. So you would have 4/5 times x. Good so far? So, and this will be the hardest one. Okay. Now, the thing to remember here is that if we were to let, we want to turn this into a vector valued function, right? So if we were to say, okay, well, R1 at t, okay, would be, so here, if we would let x equal to t and y equal to, then, good, 4/5 t. And so our first one would be t times I plus 4/5 t times j. But you got to figure out what interval that goes on, right? So here, when t is 0, it works, right? Because you would have you have the point 0, 0, and you'd have the vector 0i plus 0j, right? And so how long though is that going to work? I mean, we know that 0 would be our left bound on t, but how far is t going to be going? Beautiful. T is going to travel 5, right, on that x-axis, right? It's going to travel 5 units. And so in order to fit that first one, let's see if this works. 0 less than or equal to t less than or equal to 5. So let's try it. Do we get our end point of 5, 4 if we were to plug that in for t? So we'd end up with 5i plus 4j, and that would definitely end us at the order pair 5, 4. That would give us that vector. Cool, cool? Okay, so we're good there. So now, as t continues, right, what's going to happen? Well, we're over 5, aren't we? We're over 5, so let me get a different color for this one. So as t is going this way, traveling this way, we've got to be 5 over for all of them. And so the function of the x at t, right, is going to have to be 5, all right? So our x at t has to be 5. I mean, y starts at 4 and it reduces down to 0. So we have to have this y at t. So t is starting at 5, right? And when we're at 5, 4, we need to have an output of 4. So what if we had 9 minus t? So when t was 5, right, because that's where we're starting, 5, then you would get that, beautiful, you would get that y at t is 4, which is what we are looking for. So we've got it. We will have, for that second piece, our 2 at t would be 5i plus 9 minus t times j. And that's going from t being between 5 and then when we need, basically are going to have an output of 0, right, for that coefficient to j. So that would be between 5 and 9. Groovy? All right, and then finally, if we look at this one here, we'll have our 3 at t. So notice for this one, x can vary, but isn't y always 0, right? Y is always 0. So y at t is 0. And x at t is going to be what? Well, remember, t is starting at 9. And so basically, when we are at this ordered pair right here, which is what, 5, 0, we want x to be at 5, right? And so what should we do? Beautiful. It would be 14 minus t, right? Because 14 minus 5 is 9. And then and then we'll figure out that other edge. So we'd be going from 9 is less than or equal to t, right? Which is going to be less than or equal to, well, x at t has to be 0 at the very end, so it would go all the way to 14. Agree? So our 3a at t, this vector valued function, would be 14 minus t times I plus 0 times j. So putting it all together, and these all, they are equal at the end point, so we can keep the equalities there. I know it's kind of weird, but what we'll end up having here is r at t is equal to this piecewise vector valued function, where we'll have t times I plus 4/5 times t times j, and that's going to be from 0 less than or equal to t less than or equal to 5. And then the second one was 5i plus 9 minus t times j, and that's between 5 and 9. And then finally, we had 14 minus t times I, and that went between 9 and 14. Groovy? All right, so that gives you a couple of examples, and at least this way you had sort of a piecewise one where we made this. Remember, the whole evil plan was to find a piecewise smooth parameterization of the path C. Cool, cool? So we'll call this example 2. Actually, just to be consistent, example 1, A and B. Okay, so next up, let's look at the definition of line integral. If f is defined in a region containing a smooth curve C of finite length, then the line integral of f along C is given by the integral along C of f at x and y ds, which is equal to the limit as the norm of delta approaches 0. So norm of delta is the widest subinterval. Okay, so as that widest subinterval approaches 0 of the summation from I equals 1 to n of f at xi, yi, delta si. That's in the plane. Or if you've got this integral along this smooth curve C of f at x, y, and z ds is equal to the limit as the norm of delta approaches 0 of the summation from I equals 1 to n of f at x, I, yi, zi, delta si, that's in space, provided the limit exists. Now, to evaluate a line integral over a plane curve C given by r at t equals x at ti plus y at tj, just use the fact that ds is equal to the magnitude of r prime at t dt, which is equal to the square root of x prime at t squared plus y prime at t squared dt. Cool, cool? Okay, so theorem, evaluation of a line integral as a definite integral. So let f be continuous in a region containing a smooth curve C. If C is given by r at t equals x at t times I plus y at t times j, where t is between a and b inclusive, then the line integral along C of f at x and y ds is equal to the integral from a to b of f at x at t, y at t, times the square root of x prime at t, the quantity squared, plus y prime at t, the quantity squared. So this should look somewhat familiar, and then that's with respect to t, sorry. This should look somewhat familiar to what we learned in 7.4. We learned about arc length, and so it's a little different, yes, but we, that square root of, the derivative squared, the sum of the derivative squared should look somewhat familiar. Now, if C is given by r at t equals x at t times I plus y at t times j plus z at t times k, where t is between a and b inclusive, then, well, what do you think we'll get? We'll get the integral along C of f at x, y, and z with respect to s is equal to the integral from a to b of f at x at t, y at t, z at t, times the square root of prime at t, the quantity squared, plus y prime at t, the quantity squared, plus z prime at t, the quantity squared, with respect to t. Note that if f at x, y, and z is 1, the line integral just gives the arc length of the curve c. Isn't that groovy? So that is the integral along c of 1 ds ends up giving you the integral from a to b of the magnitude of, this should be the vector r, prime at t dt, which is the length of the curve c. Okay, so now let's look at the next example. So evaluate the line integral along the given path. So we have the line integral along the path c, 8 times x, y, z ds, and c is the vector valued function, r at t equals 12 times ti plus 5 times tj plus 3k. And t is going from 0 to 2 inclusive. So let's check it out. What do we need to do? Well, it might be nice to identify, each component and then get the derivatives. So x at t is equal to 12 times t, and x prime at t is equal to 12. Y at t is equal to 5 times t, and y prime at t is equal to 5. And then z at t is equal to 3. So z prime at t is equal to 0. Not so bad so far, right? Okay, so we've got those things. Now, now what do we need to do? Oh, good. So we need to find f at x at t, y at t, and z at t will equal to f at, so what was x at t? So f at 12t, 5t, and 3. And what was our f? It was 8 times x times y times z, right? So that would be 8 times 12t times 5t times 3. 8 times 12 times 15, enter, so 1440. All right, so that's going to be 1440 t squared. Groovy? Okay, so now let's take a look at our, well, we can just kind of put it all together, right? So basically, our integral along C of 8 times x times y times z ds is going to equal to the integral from 0 to 2, right, of, I guess I'll just write it all out. Remember, it was going to be f at x at t, y at t, z at t, times the square root of x prime at t squared plus y prime at t squared plus z prime at t squared dt. Well, this will be the integral from 0 to 2. Well, we found f at x at t, y at t, z at t to be 1440 t squared. Remember, that's from the purple. And then we got, let's see, we got those other ones individually. So we'll have the square root of, this will be a lot shorter. So remember, x prime at t was 12. So we'll have 12 squared, which is 144, plus, I'll do this in blue since we got it from the blue part. So 12 squared is 144, plus 5 squared is 25, plus 0 squared is 0. And then we still have, with respect to t, well, 144 plus 25 is what, 169, which happens to be 13, right? Is 18,720. So 18,720. I'm going to now integrate the t squared. So that's going to be divided by 3 times t cubed, and that's going from t is 0 to t is 2. So the lower limit of integration will zero out, right? And when I plug in t, I am going to get 8, right? So let's see, I think 3 is going to divide, that'd be what, 9 plus 9, 18. 3 is going to divide this stuff, so let's simplify it a little bit. 3 goes into itself once, and then into 1870, 6240. And so now I just need to multiply that by 8, and we'll get, that'll be 6240 times, I'll just say 8 minus 0 so you guys can see where it comes from. And then that will end up being 49,920. 49,920. Cool, cool? All right, so that's it. That's all she wrote. All right, so now let's check out definition of line integral of a vector field. So let the vector field f be a continuous vector field defined on a smooth curve C given by r at t, where t is between a and b inclusive. The line integral of f on C is given by, so you've got this part here, and then it's going to be the dot product between f dr, and that ends up being equal to, the integral from a to b of the vector field f evaluated at x at t, y at t, z at t, dot r prime at t dt. All right, so and you know, if you take advanced calculus, you'll be getting into all the deeper meaning of all this. I just want to expose you to it initially, you know, so you've seen it once, and so it'll be easier for you. All right, so we got to find lots of stuff here. All right, so we want to evaluate the line integral of the vector field x squared times I plus y squared times j plus z squared times k. And the smooth curve, right, that it's going on is r at t equal to 2 sine t times I plus 2 cosine t times j plus 1/2 t squared times k. And t is going between 0 and pi inclusive. So x at t is going to be equal to 2 times sine at t. So x prime at t is going to be 2 times cosine at t. Y at t is equal to 2 times cosine at t. So y prime at t will be equal to negative 2 sine at t. And our z at t is 1/2 t squared. And so z prime at t will be equal to, oh, that's nice, it'll just be equal to t. Okay, so now let's see what we've got. So that makes r prime at t equal to 2 times cosine at t times I minus 2 sine t times j plus t times k. Cool so far? All right, so now let's take a look at our vector field and evaluate it at x at t, y at t, and z at t. So when we do that, we shall have our vector field f evaluated at x at t, y at t, z at t. So for this one, we're going to have to, remember our vector field is x squared times I plus y squared times j plus z squared times k. So we're going to have to basically have we're going to have 2 sine at t, because that was x at t, and that's going to be squared, and that will be good times I, plus y at t was 2 cosine at t, so we'll have plus 2 cosine at t, the quantity squared, times j. And then z at t was 1/2 t squared, so we'll have 1/2 t squared squared times k. So that's going to give us 4 sine squared t I plus 4 cosine squared t times j, and then plus 1/4 t to the 4th times k. Cool so far? Our integral is going to go from 0 to pi, and remember that it's our capital F evaluate, or our vector field, evaluated at x at t, y at t, z at t, dot r prime at t dt. Okay, so that will equal to, in turn, the integral from 0 to pi. So when we find the dot product, we're going to have what? 4 sine squared at t times 2 cosine at t will be 8 cosine t sine squared at t, and then minus 8 cosine squared at t sine at t, and then when we multiply the others, we'll have, I believe, 1/4 t to the 5th. So I'll just write t to the 5th over 4, and that's all going to be differentiated with respect to t. Now the beauty here is that for the most part, especially if we change this one to plus a negative, right? We'll have what we need for the integrations, which is awesome. So we'll have 8/3 sine cubed at t plus 8/3 cosine cubed at t plus 1/24 t to the 6, and that's going to go from t is 0 to t is pi. Now be careful on this one. You're still going to have one term when t is 0 because of cosine 0 is 1. So let's see what we get. We're going to end up getting sine at pi is 0. So our upper limit of integration will be 0. And then cosine of pi is -1. When we cube that, it'll be negative. So minus 8/3. And then plus pi to the 6 over 24. Minus our lower limit of integration. So when t is 0, the sine function zeroes out. Cosine at 0 is 1. So we'll get positive 8/3. And then, actually I'll write it out. So we'll get 0 plus 8/3 and then plus 0. So that's going to give us pi to the 6 over 24 minus 16/3. And if you want to be fancy, you can write this as equals 1/24 times pi to the 6 minus 128. Cool, cool? All right, so either one will work. Groovy. All right, so next up, line integrals in differential form. So here we go. If f is a vector field of the form f of x and y equals mi plus nj, and c is given by r at t equals x at ti plus y at tj, then f dot dr is often written as m dx plus n dy. So this is what you'll see for this line integral here. F dot dr is going to, and then r of course is the vector, and that's going to equal to, you've got your integral along this smooth curve for of f dot the derivative of r with respect to t dt, right? So all we did is multiply by dt over dt, no biggie. But that turns out to be equivalent to the integral from a to b of, remember your vector field, substituting that in for f, you've got m times I plus n times j, that's in for the vector field f, dot r prime at t, but we often write that as x prime at t times I plus y prime at t times j, all with respect to t. So just so you can see, here was our vector field rewritten, and then here was our r prime at t. And that in turn can be written as the integral from a to b. Once we do that dot product, right, that would be m times dx dt plus n times dy dt with respect to t, which you will often see as this line integral, okay, of m dx plus n dy. And oftentimes you're going to see the parentheses are omitted. Okay, so most of the time you're gonna see it much. You're just gonna see it as you'll see it like this. Okay. I don't know why, but that's the way it is. Okay, so here we go. Example 4 has us evaluate the integral, right, along the smooth curve of 2x minus y dx plus x plus 3y dy. Notice the parentheses are omitted from the total along the path C. So what we want to remember, and then C, is the arc on y equals x to the 3 halves from 0, 0 to 4, 8. It's given in this format. And so matching it up, right, do you see that our m would be 2x minus y, and our n is x plus 3y. Cool so far? So let's find our parameterization of C, okay? That's going to be something that will be good. So parameterization of C. So if we let x equal to t, easiest thing to do, dx dt is going to be 1, and that gives us that dx is equal to dt. Cool so far? And remember that t will be ranging between 0 and 4. And that's just from what's given here, right? 0 to 4, 0 to 4. Well, if x is t, y, coming from this here, y is going to be equal to t to the 3 halves, right? And so our dy dt would be equal to 3 halves t to the 1 half. Cool so far? And so dy is going to equal to 3 halves t to the 1 half times dt. Cool so far? All right. Well, now we've got all the pieces, right? So let's scope this out. So our line integral over here will be the integral from 0 to 4, right? And those x's. And then 2x minus y, right? So remember that x is t. So 2t minus t to the 3 halves, oops, and then times dx, and dx is beautiful dt, plus x, which is t, plus 3 times y, and y, remember, was t to the 3 halves, and that'll be times dy, which is 3 halves t to the 1 half dt. Cool so far? And actually, I guess I don't need these. Well, I'm going to keep those brackets because just for form's sake. All right, so let's just match up what everything is, okay? So remember, x is t. That's from here. And remember that dx is equal to dt. And y was equal to t to the 3/2. And dy is equal to 3/2 t to the 1/2 dt. So this is cool. This is something we can work with, right? So what do we get here? We're going to end up with the integral from, actually we can just start evaluating, right? So it's all going from 0 to 4. It's all being integrated with, well, you know what, let's simplify. First of all, the dt can go on the outside, so we'll have the integral from 0 to 4. We're going to have 2t minus t to the 3/2. The dt will be factored out at the end here. And then plus 3/2 t to the 3/2. I'm multiplying the t times t to the 1/2 to get t to the 3/2. And then we'll have plus 9/2 t to the 4/2, which would make it t squared. So this I can just bring a little closer. Okay, so do we have any like terms? We do. So that'll be equal to the integral from 0 to 4 of 2t negative 2/2 plus 3/2 would be plus 1/2 t to the 3/2, and then plus 9/2 t squared with respect to t. So then that will give us 2t squared over 2 is t squared. So we get t to the 5/2 over 5/2, flip it, 2/5. I think that's going to be 1/5 t to the 5/2. And then t cubed over 3, I'll cancel out some of that 9. So I think we'll get 3/2 t cubed. And then t is going from 0 to 4. So note that the lower limit of integration will zero out. So we are going to get 16 plus 1/5 times square root of 4 is 2, and 2 to the 5th is 32. And then we have 64. So we'll have plus 3/2 times 64. That's going to give us so let's see, 3 times 32 is 96. 96 plus 16 is 112, I think. And then plus 32/5. And then we'll have, multiplying that by 5, we would have 560 plus 32 all over 5, which will be an end result of 592/5. So not so terrible, huh? Once you get it in the format that you're familiar with. So anyway, that's it for today. I hope you have a wonderful morning, afternoon, or evening whenever you're watching the show. And hey, if you like what I'm doing, please subscribe and tell all your friends. Bye.